Hi, welcome to the virtual problem solving session on shafts and shaft design. We're going to look at two problems this week, and the first problem is more of an analysis problem where you're given the dimensions of a particular location at a shaft, you're given the material properties, and you are trying to figure out the factors of safety. So we'll just jump in. At a machined shaft shoulder, the small diameter is 1.125 inches, the large diameter is 1.75 inches, and the fillet radius is 0.12 inches. The bending moment is 1,300 pound-inches, and the steady torsion is 1,100. The heat-treated steel shaft has an ultimate strength of 110 KSI and a yield strength of 85 KSI. The reliability goal for the endurance limit is 99%. I will also add that we are assuming room temp and no additional effects that may worsen fatigue. So determine the fatigue factor of safety of the design using the modified Goodman failure criterion, and then also determine the yielding factor of safety. We want to determine the yielding factor of safety because if we determine that the yielding factor of safety is less than 1, it's an indication that the part's going to fail on that first cycle of loading, and hence fatigue isn't even an issue. Okay, first step, draw a picture of the machined shaft shoulder, including dimensions. So again, we're just drawing a portion of the shaft. We're just drawing and analyzing one location. So the dimensions won't be to scale, I'm sure, but here we go. We have torsion, and then we have bending moment, and it is fully reversed, so it's going, oh, I have a straw right here. So you can picture it, shaft is kind of doing this as it's rotating. So D equals 1.75 inches, big D that is. Little d is 1.125 inches. Fillet radius is 0.12 inches. Okay. So first step, find the corrected endurance limit. So that would be SE, and to get to SE, we have to do the whole Marin equation thing, and we start with SE primed, which is the the lab value for endurance strength without all of the fatigue factors applied. And this is a simple calculation, 1/2 SUT. So this is in my analysis tool, which I'll show you here shortly. And then all of these factors are in my analysis tool as well. So let's take a look at my analysis tool. Note that I have both English units and metric units. And this sheet is also set up to do both kind of a design approach and an analysis approach. So I'm just going to be showing how I use my tool in an analysis situation, which is what we have here. So we're in English units. So I'll just focus on this input box here. So let's do the Marin equation first. I've entered the ultimate tensile strength of 110 kpsi, the yield strength 85 kpsi. SE prime is calculated automatically to be half of SUT, so 55 kpsi. Ka was based on the fact that we have a machined shaft shoulder, so you need to use the appropriate A and B constants. And make sure again that you're referencing A and B from the updated edition, so the 11th edition constants. Next, we'll look at KB, the size factor. So remember from chapter 6 that the size factor is going to depend on the diameter that you have. So if you look up at my equation bar, I have one expression if the diameter is less than 2 and another expression for if the diameter is greater than 2. So my input for the diameter is down here, 1.125. So for my KB expression, my KB is 0.879 times the diameter, 1.125, to the negative 0.107. KC is a loading factor, and we have both bending and torsion going on, so we just set KC equal to 1, and then we'll use von Mises. KD is a temperature factor. This is room temp, so this would be 1. KE is the reliability factor, and for 99% reliability, our KE is 0.814. KF, we don't have any other conditions that we think would make fatigue worse, so we set that equal to 1. Q and QS are calculated directly from the Newber equation, so I have that routine kind of up here in gray. So again, make sure you're programming this into your tool, not trying to read the charts. For KT and KTS, those are the static stress concentration factors, and you do actually need to reference some charts for that. So this is our situation for bending to find the static stress concentration, KT. Our radius is given as 0.12, so I use these little lines, try to line it up, and then our big D over little d ratio is 1.75 divided by 1.125. It's given in the problem statement. So about 1.6. I have to do some interpolating here. Here is our curve for 1.5. Here's our curve for 3. So if I imagine a curve a little bit above the 1.5 curve, I can imagine it kind of intersecting right here. And that would correspond, if this is 1.6, 1.7, we can call this 1.65 for KT. So yeah, you'll have to do a little bit of interpolation there. And then same thing for KTS. 0.12, d over d of 1.6. It's even more squished in between these two curves here, but interpolating looks like KTS would be about 1.4. So those are yellow because they are inputs. Actually, now that I'm here, I'm going to change these Q's to orange. So that's just my note to myself that these are intermediate calculations done elsewhere. Everything in yellow is something that I have to enter in myself. Okay, so KF and KFS would be calculated automatically from Q, QS, and KT and KTS. So we can record our answers, find the corrected endurance limit. So this is similar to what you would report on your assignment. And then calculate fatigue stress concentration factors. So again, KF 1.56, so that's our bending fatigue stress concentration factor. KFS 1.36, that is our torsion or shear fatigue stress concentration factor. So visually characterize the applied loads, include both shape and magnitude. So we have bending moment in pound force inches. It's fully reversed, and it's fluctuating between 1300 and negative 1300. Torsion is steady, and 1100 was our value. So that's all you have to do. So find values for the alternating and mid-range components of stress caused by the loads characterized above. So if we look at these, this is a bending moment, so it's going to cause some bending stress by our old friend, the flexure formula, and then another old friend, the shear stress formula. So what we do with this step is remember that we have to include our stress concentration factors, and we're also going to be able to use a more simple expression. We don't have to find the moment of inertia because we have a solid round shaft. So I'll show you what this looks like. So don't forget your KF. It's a super common mistake. And we can do a little simplification here. This becomes, okay, and this just is from the fact that moment of inertia is pi d to the fourth over 64. And then C is d over 2. So that's how that simplifies. Okay, and then for mid-range shear stress, KFS, for J. All right, so that's a lot of scribbling. What goes in your analysis tool? This goes in your analysis tool, and this goes in your analysis tool. Let me show you. So our alternating bending stress is 14,525 psi, and the inputs for this are KF, and the D of 1.125, and then our MA, so pulling from 3 different spots on my analysis tool. And then the mid-range shear stress, 5,339 psi, and puts our KFS, again, the diameter of the section we're interested in, and then our mid-range torque of 1,100. So you might be wondering why we don't have a sigma M and a tau A, and it's because that in our situation, these stresses are 0. So let's go back to what our applied loads look like. So in this case, our mid-range bending moment, where MM equals 0. And then in the case of our torque, we don't have any fluctuation here from our mid-range value. So our alternating torque is 0. And this is going to be the general case for rotating shafts. So you will be fine in your analysis tool if you just have sigma A and tau M. So let's report our values: 0 for mid-range stress, alternating stress 14,525 psi, mid-range shear stress 5,339 psi, and alternating shear stress 0. So we need these values to answer the next part of this question: find values for the fluctuating von Mises stresses. So our sigma prime A, when you see the prime, it's just telling you that we're talking about von Mises stress. So everything that's alternating goes up here. Everything that is mid-range goes down here in this equation. 3 tau m squared 1/2. Okay, so what goes to 0? This goes to 0, and this goes to 0. So sigma prime A is really just sigma A. Sigma prime M is not just tau M because of this 3 here. So back to my analysis tool. So sigma prime A stays 14,525 psi. Sigma prime M is now 9,248 psi. To get sigma prime max, one way to do it is just to add sigma prime A and sigma prime M, which is the approach I'm taking here. So to report values, sigma prime M, 9,248 psi. Sigma prime A, 14,525 psi. And then again, if you were reporting sigma prime max, you can just do sigma prime M plus sigma prime A. And that was 23,773 psi. So from chapter 6, if we want to report factors of safety for fatigue first, so we're using modified Goodman. 1 over the fatigue factor of safety equals sigma prime A over SE plus sigma prime M over SUT. And so just make sure in your analysis tool that you are putting this whole expression in the denominator. Make sure you calibrate your tool. So factor of safety for fatigue, 1.66, and then the yielding factor of safety is the yield strength of 85 kpsi divided by sigma prime max. So it looks like fatigue is a greater threat than yielding, and we would not expect a first cycle yielding.